Okay, I want to show you some rules of differentiation now. So this little screencast will be to do with finding out some shortcuts to finding the derivative or the gradient function, as we like to call it as well. Okay, same thing, derivative gradient function. So the rules of differentiation, I've written up a little table here, some notation. Let's be familiar with our notation. So our function notation is f of x, and often we'll see f of x equals blah blah blah, and in that case our notation will be to find the derivative f dash x equals, and we'll apply our derivative rules that we'll discuss in a moment. If the function is written y equals, now these are interchangeable, function notation and sort of old school y equals. If it's y equals, then we follow up with dy dx. This means the derivative of y with respect to x, or just y dash. I guess I know which one you'll choose, but they're both valid. Okay, and just underneath here, sometimes we'll see it, you might see this. This says, as I've translated underneath, this says the derivative of this function with respect to x, which is important. So this here, this little x here, or that variable, has to match that one, otherwise you're in trouble. Okay, so that says if the derivative of x, the derivative of this function with respect to x equals f dash x. So this is the derivative. So that's the translation, is f dash x, right? So that's, if you see this, what you need to do is just derive this thing that's in the brackets. Okay, so let's get to the rules. Right, we did a quick, in the last 5 minutes of Friday's lesson, we looked at some of the questions that we'd been looking at. We did some of those first principles questions where we had to find the limiting value of functions. We put 2 or 3 together and we figured some rules. So what were they? Okay, so if we've got a function that's x to the power of n, then this power rule suggests that we bring the n down here. Right, the n comes down, x holds obviously, and the power of n reduces by 1. So the derivative of x to the n will be nx to the n minus 1. So example, the derivative of x to the power of 12 is equal to 12x to the power of 11. That little 12 came down, x to the power of 11. Okay, just beneath it, we've got now a constant a here. Then the f dash x, this is one we talked about on Friday, will be a by n x to the n minus 1. So in this example, we've just got a 3x to the power of 4, that sort of thing. Let's derive 3x to the power of 4. 4 comes down, multiplied by 3. It's not always 12 out the front. 4 3s are 12. X, reduce the power of 4 by 1, 12x cubed is how you'd go about that. So they're the rules for differentiation. Not a lot more to it. We looked at constants, what happens to constants. They went to 0, didn't they? So we could just have a look at that. So what do we say there? If our function of x is equal to c being constant, then f dash x was equal to 0, wasn't it? So if you think about c, right, c is just a constant, then we could write it as cx to the power of 0, right, because x to the power of 0 is 1. If we apply this rule here, where we take the power down and multiply by c, this one here, take the power down, n by a, in this case it's 0, so that's 0x, doesn't matter, we could put that to the minus 1, doesn't matter, 0 times anything is 0. So any constant will derive back to 0. Makes sense. Let's think about it. If we're looking at a function of x equals to a constant, what is that? That's a straight line, isn't it? So f of x equals 2, say, is a straight line, horizontal line. Sorry, I shouldn't say straight, horizontal line going through 2. What's the gradient of that line? Gradient is 0, isn't it? So, and this is, remember, f dash x, gradient function. That's what we're getting. We're getting the gradient. Let's not forget that. Okay, what about the linear arrangement? So if f of x is equal to, let's say mx, m being a constant. I'm using m because m is the, back to y equals mx plus c days. Then what's f dash x here? We did one of these examples by first principles. It's equal to m. It's the value of that coefficient. Again, mx, what's that? That's a straight line, isn't it? Straight line with gradient m equals m. And what's its gradient function? Always m. So we talked about that on Friday. Okay, that's enough of that stuff. Let's do some examples. Pinching from your textbook. We're looking at page 203 here. So I'll pause while we do some examples. Okay, so let's have a look at some examples here. It's the task is to find the derivative or gradient function, same thing, of each of the following. Right, so firstly, 1 over x cubed. We've done some really simple examples, x to the power of 12. I think that's the first one actually. I missed that because that's pretty straightforward. So before we get into deriving this, we need to get this looking like so. We need to get it looking like this. So we need to see coefficient base, which is x, and power. Now, all right, so let's rewrite this as x to the minus 3. Now we can see coefficient 1, base and power, and now I can say therefore f dash x equals minus 3 pops down, x holds, subtract 1 there, don't we? So minus 3x to the minus 4, and if we wanted to be clever, we could rewrite that with a positive index as minus 3 over x to the power of 4. Perfect. Okay, go to question example 2. Let's say y equals the square root of x. Okay, so again, let's get it looking like this with a power there. Can't have this square root of x business. Let's write it as x to the half. Hopefully you remember that stuff. Alright, so now I'm ready to derive. I can't just write equals the derivative because that wouldn't make sense. I'll write y dx or y dash equals. Let's bring the half down and subtract the half by 1. What do I get up there? Minus a half. Half x to the minus a half, which is correct. I've derived it now, but now let's just tidy it up. What's this equal to? A half times, this is x to the minus a half, which is 1 over x to the half. We could keep going, couldn't we? A half times 1 over square root of x, just get it back in square root form, which is 1 over 2 root x. 1 over 2 root x there for our derivative function, dy dx. Okay, continuing. Question, let's have a look at example 3 here. So differentiate y equals 4x cubed. Now if we've got more than one term, we just deal with each term individually. So y dash will equal 3 4s are 12x, reduce the power by 1. 2 2s are 4x, reduce the power by 1. 3 goes to 0, so that's done. So the derivative function there is 12x squared plus 4x. Tell you what, I'll put this example down. I want you to see if you can answer it. Actually, yeah, I want you to always sort of take this approach. 3 by the 5th root of x. Right, so write this example down. You should be taking notes anyway. This is 3 by the 5th root of x plus 8. Okay, and just see if you can rewrite this in this form, in this format here, so that we can derive it. So have a go at deriving this function, and then press play again. Okay, hopefully you've already had a go at it. So I'm going to rewrite this as 3 by x to the power of 1/5. That's the 5th root of x, isn't it? Plus 8. So now I'm ready to derive, so I'm going to say f dash x equals 1/5 comes down, times by the 3, that's 3/5 x. Reduce this by 1, what's that? Minus 4/5 plus 8. 3/5 x to the minus 4/5 plus 8. Now I could say that's 3/5 by 1 over x to the positive 4/5. I'm not going to get a lot more out of that. That would be 3 over 5 x to the 4/5 plus 8. Why did I write that plus 8 there? That's an error, isn't it? Hopefully you're shouting at the screen saying, what are you doing, Sherwin? Because that's incorrect. Once that 8 derives to 0. So I'm just left with this as my derivative function. Let's have a look at 2 more. Question 5. I want to derive this function here. X minus 2, x plus 4. Okay, I'm not ready to derive it yet. Thanks very much. I'll do some expanding. X squared plus 4x minus 2x, that's plus 2x. Minus 8. Now I'm ready to derive. It's in the format I'm happy with. I've got 2x plus 2. Brilliant. Alright, 6. Last one. Now, alright, this is a different question again. 4x cubed plus 2x squared minus 3 over x. Okay, now the technique here is to split this fraction up. So I've got 4x cubed over x plus 2x squared over x minus 3 over x. So I split that up into 3 separate fractions. Now I can rewrite each in simplified form. And this is minus 3x to the minus 1. Now it's in a format for me. This should be a y equals. It's in a format for me to derive. So our derivative function is now 8x plus 2. Oh, what's happening here? Minus 1 comes down, so it'll be plus 3x, subtract the power by 1 minus 2. I could leave like that, or I could tidy it up if that was my wish, to plus 3 over x squared. Okay, 7e and 7f are going to be ours for the taking on Monday when I see you. Exercise 7e and exercise 7f. I can tell you now, I think we'll be doing all of them because there aren't that many, and we need lots of practice at differentiation to get really good at it. Okay, I'll see you soon.